Hello, so today we are going to do this problem, which is part of weekly contest 346. This is problem 3. Find the punishment number of an integer. So basically here we have an integer n, and we want to return this thing called punishment number. And we define that number as the sum of the squares of all the integers I, such that this integer is between. So we take the sum of the squares of all integers that fit these two conditions, and those integers each need to be between 1 and n, and the product, so let's call this integer I, so I multiplied by I, can be partitioned into contiguous substrings such that the sum of the values is equal to the number itself is equal to I. A little bit convoluted, but let's see an example. So we have n equal to 10, so that means we want to look for the integers between 1 and 10 that have this condition. Okay, and so there are exactly 3 that have this. The first one is 1, because if you do 1 multiplied by 1 you would get 1, and 1 can be partitioned into just one, the value 1, which is equal to I itself, and so we count that. And then the second example, that the second number that has that condition is 9, because if you do 9 multiplied by 9 you will get 81, and 81 can be partitioned into just 8 and 1, and then so these are the two contiguous substrings, and if we get the sum of those we'll get 9, which is equal to I, which is 9. Okay, so that's the idea here. And then the second one is 10, because 10 multiplied by 10 is 100, and 100 you can partition it into 10 and 0, right? So you basically cut here, you get these two partitions, and if you sum these up you get 10, right, which is the initial number. So that's also valid, and these are the only two numbers that are valid between 1 and 10. And so the total is of the square of these numbers, so the square of 1, 9 and 10 is 182. So that's the idea here. Now if we take a look at another example, 37, we already have the 3 numbers that are have the valid condition, which is these 3, and those are in the range 1 to 37, so include them. But we also have 36, because 36 multiplied by 36 is this number, and this number can be partitioned into 1, right, 2, and then 2, 9, right, and then 6. Okay, and if you sum these numbers up, you get 36, because 29 plus 1, 30, 30 plus 6, 36. So it's valid, and so we include it, and then we get the sum of the squares, which will give us this number. Okay, so that's I hope that makes the problem clear. The values are not too big, up to 1000, so we should be able to do a non-super efficient solution. So let's see how we can tackle it. Okay, so let's see how we can tackle this. So let's take the first example where n equal to 10. So these numbers can be up to 1000, so that means we can actually just go through them from 1 to n. It should be efficient if we don't do too much in the check. And so here we'll just go through these numbers from I to from 1 to n, right? So here it would be 1, 2, 3, all the way up to 10. Okay, and now we want to check if we can partition this number, just the second condition that we have. So we want to check if we can partition it such that the condition is valid. Okay, and so our condition is that I multiplied by I, right, if we can be partitioned, the string of this can be partitioned, right, into numbers that when you add them up you get I. That's what the problem asks us to do. So we want to check if we can partition this according to this condition. If we can, then we want to just add it to the total. And what's the total that we want to return? Well, the total is just going to be the sum of the squares of these valid numbers, and so that's just going to be the sum of the squares of these. Okay, so I to the power of 2, and then at the end we want to return this. And so now the meat of the algorithm that we want to find is to find the actual logic for partitioning. Okay, so let's take first just a small example with 81. So let's say for I equal to 9 we want to check, and so we by 9 is 81. So we want to check if we can partition this. And so how do we do that? Well, we just try all partitions, right? So what are the partitions of 81? Well, you could do 8 and 1, or you could do 81, right? Those are the only two options. So how do we do this? Well, with partitions, you actually have only two choices each time, right? And so let's actually grab a bigger number so that it's a little bit more clear. So let's take I equal to 36, right? So 36 by 36 was 1296. Okay. So with this number, what are the choices? Well, we have first this one, and then we have 1296, and we have 1296, and you get the idea. We have multiple. And so how do we do this with partition? Well, this is a good like recursion or backtracking sort of solution. Well, let's take 1296. Each time we have two choices, right? For each number, we can either include it in the previous partition or start a new partition. So for example, for this 2, once we have the partition with just 1, we can either decide to include it in the current partition or start a new one and have 1, 2, right? So that's exactly what I want to do here. So here we have to start a new one because there doesn't exist anything. So we just put 1. Okay. And now we want to decide from here, do we want to include 2 as part of the current partition, or do we want to start a new one, which would mean we have like this. So those are the two choices we have here. And then once we do this, what about 9? Well, we can again choose to include it in the current partition, get 129, or choose to have another partition, so 12, 9, like this. And then after that, we'll look at 6. Again, do we want to create a new partition or start another one? And so if we want to continue the current partition, we'll get like this. Start another one, we get 1296. And so you can see these are two valid ones. Here we can do 196. And so you can see with this example, we got 1296 here. Okay. Or the other one, which is 129 like this, which is this one. Okay. 1296. Not that one actually. It's 1296. This one. That's this one. Okay. And then same thing here. We choose either to have 126. We choose either to include in the current partition, which is actually 9, so 96, or start a new one, which would be 1296. Okay, and we keep doing the same thing. And so that's sort of the idea here. With this backtracking, we have only two choices each time. And so choice 1 is include in current partition. Okay, or choice 2, start a new partition. Okay, and then once at the end, what do we want to do? Well, we want to just get the sum of these partitions. So for example, with this one, 129 plus 6. Okay, and we want to see if this is equal to the initial number I, which is 36. So this is our target. So we want to check that. And if we do this in this problem, we will, once we get 129, 6, let's see, where do we get 129? So if we do like this, for this one too, we have two choices: either include in the current partition, which would be 129, or start a new one, which would be 129. And from this one, we will choose either include in the current partition 96, or start a new one, which would be 1296, right? And this is the one that we have here, the right solution. Okay, and so now with these two choices, let's see what would our function look like. So let's call our function partition, and let's think about what are the inputs we need. So the inputs we need for this function are, of course, we want to, because we call it for each one of these, we want to pass it I. Okay, so let's call that the target, because that's what we want to check if the sum of the partition is equal to I. Okay, so let's call that target. And then we want to pass I multiplied by I, because that's the thing we are partitioning, right? So let's call it S, or whatever you want to call it. And then here, each time, what do we pass to the child? Well, when we did 1, we passed 296 because this is the remaining portion we want to partition, right? And then at 1, 2, what's the remaining portion we want to partition? It's 96. And then here, what's the remaining we want to partition? 96, so we pass it. And then here, what's the remaining that we want to partition? It's just 6. So you get the idea. Each time we pass the remaining string that we want to partition. And so here, instead of calling it S, we call it the remaining string, right? Now, what else do we need? Well, each time we have either, we want to pass the current partition, right? Because that's the one that we want to either add to or start a new one. So for example, we want to pass 1, 2 because we may decide for 9 to either add it like we did here or start a new partition. So we want to pass the current partition. Let's call it current here. But the other thing we want to pass, remember, we are adding the sum. So instead of passing the entire list of the partitions so far, right, each time we can just pass the sum. So for example, when we are at, let's grab, when we are at 129, okay, and the remaining string is 6. We actually just need to pass the current partition, which is 9, but then the sum 12. Because we have just 12. Now what about a partition like 129 and we have 6? What do we want to pass? Well, we want to pass the current partition because we want to decide if we want to do 96 or 96. But for these two, we don't need to pass the entire list because that would be too big. We just need to pass the sum, which is 3. Because at the end of the day, what we want to check is that the sum, if it's equal to I or not. So here we just will pass something called the sum so far. Okay? And that's sort of the state of our recursive function. Now, how do we change these values depending on 1 or 2? Well, target doesn't change. It's always the same. The remaining string each time we want to, once we process the first letter, because let's say we pass 296 and we process 2, we decide to put it in the current partition or the new one, then the remaining is 96. And so each time the remaining is going to be from 1 to the end. We want to pass the remaining portion. Now the sum so far, that's where it changes depending on 1 or 2, right? So if it's 1 where we include in the current partition, then the sum so far doesn't change, right? So with this example, 1, 2, 9, for 6, if we want to decide to include it in the current partition of 9, and the sum so far we have is 3, the sum doesn't change. So the current partition will become 96, but the sum doesn't change. It's still 3. And so in that case, it's just going to be sum so far. But in the second case where we want to start a new partition, so we want to have 9, 6. So let's say maybe our example had more numbers. Let's say 8 here, 5 remaining. Then we want to add this 9 to 3 so that it becomes 11. So that in the next iteration, 12. So that in next iteration we pass 12 and we pass the new partition, which is just 6. And the remaining thing is 85, right? Because we are once we start a new partition, we no longer will add to 9 to the partition with 9. And so we just pass it with the sum so far. So in this case, we want to do sum so far plus the value that we just did, which is going to be just the remainder of string at position 0. Of course, we want to convert it to an int, but that's just a detail. And then, so now we know what each function would be, what each parameter would be for these two conditions, except current. How does current change? Well, current is for 1, because we are continuing the current, let's actually just put this a little bit to the side so that we can, it's easier to write here. So with current, we have 2 choices, right? Either we include in the current partition, so this is the current partition. So let's grab again our example of 129 and we have 685, okay? So for 6 here, what do we want to do? Well, in the first one, we want to make it 96 if we include in it. In the second one, we want it to be 6. So for the first one to get this, so we already had only 9. To make it to add 6, we need to multiply this by 10 and then add 6, right? Because we are adding to a number. And so here, this is going to be just current multiplied by 10 plus the number, which is just the remainder of s at 0. Okay. Now for the second one, we are starting a new partition, so it's just going to be the remainder of S at 0. Sorry, I made a mistake here. This is not the one at position 0. This is just the current value. The previous partition, right? That's what 9 is in this case. Okay, and this is what we want to pass for the current partition, because that's what 6 is. Okay, I hope that was clear. It's a little bit, it may take you some time to just like write it down and write the different components, but it should be straightforward once you do. So let's code it up and make sure that this passes. Okay, so let's code up the solution we just saw in the overview. So what we need is first to just go through the numbers 1 to n. In Python we have to do n plus 1 to get to n, and then we want to check if we can partition to a valid partition, right? So we give it the target that we want to check, we give it the string I multiplied by I, because that's what we want to check if we can partition, and the sum initially is 0, and the first partition initially, let's just go with 0, so that if we add anything, it's going to be the first number. And then if it's valid, then we want to add it to the result. Remember, the result is just the sum of the square of all the valid partition, of all the ones that have the condition valid. And so that's what we want to return. And now we want to just write our partition function. So we said we need, so I is the target that we want to check, and then this is the remainder of the string that we want to partition, and then first we have the sum so far of our partition, sum partition so far, because this is what we want to check at the end if it's equal to target, and then we want to have the current partition. Okay, and now what's our base case? Well, our base case is when the string is empty, there is no longer anything to partition. So for example, in this example here for 36, let's say for I equal to 36, then I multiplied by I would be this. Okay, so this is the reminder of S. Each time is going to be either first 1 to 96, and then once we put 1 in a partition, we would have 296 remaining. Once we put 2 in a partition, we would have 96 remaining, and you get the idea. And so here, once at the end, once nothing is there, it's an empty string, we are done, we already partitioned. And so in that case, we can either check length equal to 0 or check it like this. So in that case, we want to check if we had a valid partition, return true, if not, return false. So how do we check? Well, we have a valid partition if the sum is equal to target. Remember, target is this I here, right? Because the problem says that it's a valid if the sum of the partitions of this is equal to I, and I is what we pass, is the target. So how do we get the sum? So the sum is the sum of the partition so far plus the current partition. So this is actually the sum of partitions, S, partition parts, or whatever you want to call it. And this is the current part, or current partition, whatever you want to call it, current portion, right? Let's call it, actually. Maybe that's better. Okay. So what do we mean by this current part? So at the last position, we may end up with, let's say, 129 as the... so let's say the current partition we have is 1. The partitions we had before is this. And then we partitioned the last one as 6. So the sums of the partition so far is going to be equal to 12 plus 9, right? Which is going to be 21. And then the current portion would be equal to 6, right? And then it's going to be the sum of the partition so far. It's going to be 21. And this 21 is coming from this previous way of partitioning. So to get the sum, we just take 21 plus 6, and that gives us, we check if it's equal to the target, which is 36. Okay, in this specific 36 case. Okay, so that's the idea here. And now we want to just do our two choices, which are either include in current partition or start a new partition, or new portion, let's call it. Okay, And so how do we do that? Well, if any of them is true, if any of them leads us to a valid partition, we want to return true. And so that means between the two, we want to use OR. And so let's just write we already saw in the overview how the parameters change. And so let's just copy that. So we said that target doesn't change, right? We always want to check against this I. So let's put it up. But the remainder here changes because we'll decide for the first position. Let's say here we'll decide for 2, and we'll pass 96 to the next iteration. And so that's going to be, to pass it, is just going to be the after taking the first position. Okay, for both. Now what about the sum of the partitions so far? Well, that depends. So I'm going to first do the include in current partition. And then in the second one, I'm going to do the start a new partition. Okay, so we said that if we want to include in the current partition, then the sum of the previous portions doesn't change. So the sum so far doesn't change. But if we want to start a new portion, then the sum we need to add the current portion because we are starting a new one from scratch. And so to do that, we want to just add the value of that current portion, right? And then for the current portion, right, here we are including in it. And so we just want to include in it let me just put this down here. So we want to include it, so we want to add it in the current portion, which means we want to add the value at position 0, right? But this is, let's say we had maybe 1, 2, right? Let's say we had 1, 2. And we want to add 9 to the current partition. So we want to make this 1 to 9. Okay. So what do we need to do? Well, we need to multiply this by 10 and then add 9. And so that's what we'll do here. And this will give us 129, which is exactly adding to the current partition. And so here we want to multiply by 10, then add the value. And actually, just to make this easier to read, let's make this value become int. This is the number. And let's add it here. Okay, and if we want to start a new partition, we just start it with the number. Okay, so including it does this, and then starting a new one does this. Okay, and that's pretty much it. Those are the two choices we have. So let's run it. Looks like we just need to do that, and let's fix. And it looks good. Looks like it passes. Let's submit. And that passes. Now, granted, this here may be 2 to the power of n, right? And so it could be 2 to the power of the length of actually s. But even if it was 2 to the power of n, the limit would be still valid because n is very small. So this should pass without a problem. Yeah, so that's pretty much it for this problem. The key idea here is first to know that you can brute force. You could just go through all of them. And then the second key idea is actually just the choice of to include in current portion or start a new one. And you just have to be very careful with the parameters you pass for each. Yeah, and so that's pretty much it for this problem. Please like and subscribe and see you on the next one. Bye.